as you all know, like hand-drawn animation or animation in general is very closely linked to filmmaking. So people think of it as a genre, but it's not, because genre is something which has more to do with the flavor, as you would say, like comedy is a genre, or horror films, horror is genre, and these kind of things. But when I say animation is closely related to filmmaking, what I mean is that when the camera was invented, basically, the way camera functions is that it records a sequence of images and it plays it at a very fast speed, and it registers to our eyes as movement, right? So even the way we look at films today, it's the same. Even if it's digital, it's still 24 frames or 30 frames per second that it plays. So people over the years realized that instead of having the camera record the frames, we could actually draw the frames. And if we play those back, it can give us a sense of movement as well. So in that sense, animation is a medium of filmmaking, right? So to understand how to do hand-drawn animation is really just how to replicate life, you know? So we all know that life doesn't really move per second or frames per second. It's just a way that we perceive it, right? So
Yes.
You can do it 24 frames, you can do it 30 frames per second, you can do it 60 frames per second, which is like super high frame FPS, which you can get these days. So the idea is that there's a term in science called the persistence of vision. Have you guys heard of it? Right? So persistence of vision, what it means is that when the light falls on your retina, basically you hold that image for 1/16th of a second in your head. But anything that plays faster than 1/16th of a second will register as just one thing. So those images get clubbed together and it just feels like it's moving. So to understand how you do hand-drawn animation, you just really need to understand how we perceive movement, basically. So I guess I'll just start sharing my screen now. Can you guys see my screen?
Yeah.
You can, right?
Yes.
All right. So I guess most of you must have heard about those 12 principles of animation and how Disney changed and made an evolution of how animation is done. But even though they're good, I'm not really bashing them. But what I found is it's maybe a very roundabout way of looking at how movement works. It may make some sense in the way that they documented it, but I still find that what they were really trying to say is just trying to define how movement works, because animation in its essence is just an exaggeration of life, right? So exaggeration does not necessarily mean that you make everything cartoony and you make everything jump around, but exaggeration is more like, you know, when you're reading a book and if you highlight a line just so that you can remember it later on. So when you're preparing for your exams, for example, you don't have to read the whole paragraph. You can just read those summary, which is the essence of the chapter, for example. So when you exaggerate something or when you caricature something, it's more like capturing the essence of it. So instead of, let's say, reading the whole chapter, you can just read the summary of it and you get the gist of it. So when you do animation, it's just like that. So like I said, when we look at life around, we are not looking at frames moving per second. It's just very ephemeral and ethereal. You know, you don't really know how movement happens, but the way we perceive it is just how a camera looks at it, basically, right? So here, as you can see, there are 12 principles, as they call it. There's caution, stretch, anticipation, staging, and all of those things. But I think out of all these, there are only 3 or 4 which really deal with how movement works. And I think it would be, say, the first one, arcs, probably, slow and slow out, timing. That's it. The rest of it I think there if you look at appeal, for example, appeal, first of all, the word appeal doesn't really mean much, like in definition. It can mean different things to different people. But appeal, as someone would describe it as something which can convey a meaning, or something which can read clearly, or something which looks very appealing, that hooks you to it. But it's very vague, and it's mostly a term you could relate to drawing, let's say, because a drawing could be appealing, like the way you draw it or something like that, but it's still very vague. Then solid drawing, of course, it has got nothing to do with movement, but it's just the way you draw. And of course, as animation evolved, now you don't even need to draw, like in 3D and in Puppet, you can do the animation without this understanding of solid drawing. So as you can see, it's not really a principle of animation, but it's more a principle of how you perceive volumes. Again, it just comes to our perception of life, And then exaggeration, again, like exaggeration, I was saying it's more how we perceive and how we capture the essence of something. It still has got nothing to do with movement, let's say. Timing is something which is related to motion, because how long something takes is the number of frames that we do. Well, we'll get to that later on. So this is something which is definitely related to animation, I'd say, like movement. Then secondary action, we'll get to it later on. It's just a very fancy label for something which is very obvious as you move along. So let's forget about that as well. Arc. Arc also can be understood as something useful for motion, because in real life, as things move, they don't really move in one straight line all the time. As I'm speaking, my hands are moving in an arc, as we talk, as we move. We'll also get to that. So everything follows a path, like a flowy path. So that is the arc of something. Like when something moves, it follows a path. So that's also related to motion. Slow in, slow out, it's also something related to timing, but it's also called spacing. So we'll get to that as well, which is also something related to motion. Then follow through and overlapping action, it is related to motion, but it's, how do I say? It's more got to do with the physics of things, like how things move. And this follow through and overlapping action, and anticipation, and squash and stretch, even all those things can, even slow and slow out, even timing, these things can be understood with something that we call inertia. Have you heard of this word before? Inertia? Yeah. So inertia is basically the tendency of objects, or the tendency of bodies to remain at rest or in motion, right? So, for example, this pen here, although you can't see it, but just take me, for example. I won't move until either I move myself or something hits me, or let's say this pen here, if it was on the table, unless I hit it, it's not going to move. So inertia means that anything which is at rest will remain at rest unless something pushes it, or if it's alive, it moves itself, right? So that, and squash and stretch also is something related to inertia. It's how bodies tend to keep moving or keep being at rest until and unless something stops them. So we'll get to that as well. So yeah, just to recap, what I'm trying to say here is that out of those 12 principles of animation, they are just ways of understanding how things move, really. All right. So we will cover those as we go through the whole workshop of those 10 weeks. But just remember that none of the animators, none of the professional animators you would meet would know all the 12 principles and be like, oh, I'm animating the shot. Am I applying all those 12? Did I miss 2? Am I just using 8? It's nothing like that, because these are just labels and these are just ways of understanding how things move. So that's it. So today we'll just focus on timing spacing, which is flowing throughout, and arcs. All right. So these three, we'll focus on these. Now, timing, as I was saying, generally we animate 24 frames per second, right? Which is, we draw 24 drawings, let's say, and if we play them, it will play as 1 second. So timing is very closely related to how long something takes. Okay. So let's say, for example, this ball. Let's say it takes around 8 frames, all right, to move from this position to this position. So if I play it, that's how it plays, right? So timing is this window of time. So if something moves at 8 frames, then 8 frames is its timing. So it takes 8 frames to go from one spot to the other. So that's the timing of it. And spacing is how those, just a second, spacing is how those individual drawings are spaced out. You see that? So here, as you can see, the spacing is fairly constant. So it's like evenly spaced out. So for example, if let's say this ball, it takes 16 frames to move from here to here, right? So 16 frames is the time it takes to move, and the spacing would be, as you can see here, how those individual drawings are spaced out. It makes sense, right? So now you can obviously see, if I play those two together, which is like the first ball, this one, which took 8 frames to move, and the second ball, which is this one, which takes 16 frames to move, you can see the more frames there are, the longer it takes, right? So I'll just quickly write it down so that you can see it. So this takes 16 frames, and this takes 8 frames. So as you can see, the more the frames, the longer it takes, and the fewer the frames, the faster it happens, right? So we can conclude from this that more frames means longer time, and fewer frames is lesser time, basically, right? So if you want something to move quickly, you can reduce the number of frames. But if you want something to move fast, take longer, you can increase the number of frames, right? And it's also fairly obvious, because if we're playing 24 frames per second, which means 1 second is 24 frames. So anything less than 24 frames would play faster than 1 second, So 12 frames would just play in half a second. 24 frames would play in 1 second. 48 frames would play in 2 seconds, right? So as you keep on increasing the number of frames, the longer it will take for that movement to happen, right? So this much is clear to everybody, right?
Yeah.
Cool.
Clear.
So just so that you have this image registered in your heads. So more frames is longer time, fewer frames is lesser time. Now let's take these two now. Now here, as you can see in my timeline down below, both these balls take 16 frames to reach here, right? So from frame number 1 to frame number 17. So that's 16 frames. So when I play those, let's see what happens. Now you can see, even though the timing is the same, but the movement is very different. And can any of you explain why this is happening, or what could be the reason?
Yes, spacing is different between the drawings. That why.
Exactly.
Yeah.
And
Because of slow in and slow out, I think.
right.
Yeah. One is linear.
Sorry.
The lower down is linear. It have linear motion.
Yeah. Linear. I mean, yeah, both of them are moving in the same line. So in one line, so we could say it's linear, but it's more constant. You can say, right?
Yeah.
So now if we
The,
take a
the,
look
the
at
spacing is linear. That yeah, constant spacing.
yeah. So if you look at the spacing, you can see that the one below this one, it has a constant spacing, because of which it is moving like in a robotic way, like so it just stops, it just starts and stops very unnaturally, because this is not how things move in real life. Because and you don't really need to know science to know these things, because you have been alive for what, 20, 30 years, so you know how things move just by observation. So again, it boils down to inertia. So inertia is like, if something has to start moving, say for example, you are in a car, okay, and you start the car, you can't just go, just as you press accelerate, you can't go like 60 kilometers per hour directly. You slowly start, then you go 0, then you go 20, 40, 60. Then after a point, you hit 60, then you can move at a constant speed. You can go at 60 kilometers per hour, but then again, you get a red light, and then you again decelerate and you slow down and it slowly stops, right? So that makes things look much more natural. So as you can see here, the top one, it has those things happening for it. So what happens here is, as you can see, like some of you are pointing out right now, it has slow in and slow out, which is also one of those animation principles. But it's basically just spacing, but in a certain way. So inertia would say that if something is at rest, for it to start moving, a force has to work on it, and slowly it will build up momentum, and it will start accelerating. And if it has to stop, it will slowly start decelerating, and then it will come to a halt. So it can't just go at a constant speed and start, and constant speed and stop. All right. So anything which has to move, it will accelerate first, and anything which has to stop, it will decelerate. And in between, it can move at a constant speed. Like I was giving you the example of a car. Even if you look at here, like you can see in the middle, the spacing gets kind of constant, right? So it's just that once it has started accelerating, then it reaches a peak. Let's say if you go full throttle on your bike, there's a speed limit to it, right? 200 kilometers or whatever. And you can't go beyond that, because that's just the horsepower that your bike has, for example. And then after that, you can only start decelerating and stop. So that's generally how things move. So from the spacing of it, we can conclude, like you can see the movement in the middle, it feels a lot faster, while the movement towards both the ends, they feel kind of slower, right? So we can conclude that the closer the spacing is, the slower the movement, and the farther the spacing is, the faster the movement, right? We can say that, right? Cool. So I'll just write it down. So closer spacing would mean slower movement or motion, and farther spacing would mean faster motion. Right? So we can see, as in this example, even though both the balls are moving at the same timing, which is both of them are covering the same distance in the same time, but the way the spacing is kept, it can move slower or faster, you know. So that is something that spacing controls. So again, to recap, timing is the window of time. It's the number of frames something takes. So if I say something takes 1 second, it doesn't really say if it's gonna go there fast or slow, you know, or at a constant speed. As you can see, that really depends on the spacing of it. If something takes 1 second, we're just broadly saying that the window of time it needs to move from one place to the other is 24 frames. But does it go like this, or it goes like this, or it goes like this? It depends on how you space those drawings, right? That much is clear. So
Yeah.
the number of frames control how long something takes, and the spacing controls how fast or slow something happens. Both of them are very related. That's why they are very difficult to grasp. And even a lot of professionals interchange those terminologies when they mean the other. You know, like people would call timing as spacing and spacing as timing. But again, these are just labels, but it's just for you guys to understand what they stand for. Now, there's another thing that we can conclude from this because of inertia, that in real life, things can only move 3 ways. Either they can stay still, or they can accelerate, or they can decelerate. All right. So either they can start slow and move fast. So this is acceleration, or they're already moving, then they can only slow down and stop, or they can move at a constant speed like we have below here, right? And the fourth way is just the object is still, right? It's not moving, it's just still. So it's just there. So again, just to recap, things only move in 3 ways. So either you can accelerate, or you can decelerate, or you can move at a constant speed. So generally, when you see your animation, and sometimes you feel like, yeah, it's playing well, but I don't know, it feels kind of choppy. It's generally because the spacing of it is not either of these three, like it's haphazardly placed. Let's say, for example, if I start animating this ball and so if I take this ball, for example, right? Now, I just keep going with it without really thinking about acceleration or deceleration. But I'm just thinking that it has to go from here to here in 16 frames. But I don't really have any plan about it. I just think that as soon as I reach the spot, I have to slow down now. So I just keep slowing down, slowing down. But now I see that I still have a lot many frames to add. As you can see, I'm only 10 frames in, but I already reached there because I wasn't really thinking about the spacing of it. But now I still have, what, 6 frames to add. Then I just keep going 1, 2, 3, 4. But it's basically just stopped there. Now, I know it's a very exaggerated example to give, but generally it's just the spacing which makes things look very choppy. So now if I play this, you can see it has like no proper acceleration or a constant speed or a deceleration. It's just haphazardly placed, you know. And by the way we went about doing it is like we just went from frame number 1, then frame number 2, then 3, then 4, then 5. This is also called animating straight ahead, which means that you don't really have like a target drawing that you have to reach. You see, you can just keep on adding the drawings consecutively one after the other. Although you can animate in this way and be super precise about it as well, but there are some limitations to it, which I'll get to. So yeah, it's the spacing which really makes or breaks how smooth. People say how you animate so smooth. So smoothness, generally, the way I see it, really boils down to the spacing of things. The timing, of course, because it is the window of time something takes, but how you place those drawings within the window of time, how closer together or farther apart they are, that makes something smoother or faster. Cool. So that's timing and spacing. Now, what do we see? Yeah. So if we animate straight ahead like we did here, although it was like done super quickly, but the problem with animating straight ahead is like you don't really have an end point to reach, and so you can't really decide how to space it out. You see? So a good way to go about it would be to, let's say, if I just duplicate this layer first. Decide how long it takes. All right. So here, this one. Yeah. So first I decide that, okay, I know that this ball has to move from here to here in 16 frames. So that's my timing, which I've already decided. Now what I do is I put right in the middle, I put another drawing. So let's say if from here to here, I have to move, I'll just put one drawing here. Okay. So I'll just switch on the guide layer. That's it. I'll just do one thing. Copy this. Okay. So I'll just place my ball here somewhere in the center. Right? I'll try to be as precise as I can. So now I already know that halfway through it has to be here. Now what I'll do, again, I'll go back and break it down even further. Now I'll just add another drawing here, let's say. Right? So if I go in and I add another drawing here. Similarly, here as well, I'll go and add another drawing here.
Hello.
Hi.
I have a question. So should I ask right now?
Yeah, go for it.
How did you decide the 16 frames, that it will take 16 frames? It can be done in 12 frames or 24 frames, right?
Yeah, it can be. But there's also one very specific reason for which I went for 16, which I'll get to. I'll get to it soon.
Okay. Thank you.
But yeah, good question. So now, you know, I have put these at a fairly constant spacing, but now I have to make them decelerate, right? So what I'll do is here, I'll start favoring the previous drawing, which is the green one. So instead of putting, let's say, the drawing in the middle, which would make things very constant, what I'll do is I'll put it favoring the previous drawing slightly. All right. So I'll go in and I'll add this here. Okay. Now I can keep breaking it down. Now again, I'll add another one closer to this one. Similarly here, I'm constantly checking if it has to accelerate, the spacing has to increase as we move, right? So the next drawing I'll put it somewhere here. Okay. And then again, we put here, I think in the middle, we can go at a constant speed. So I'll just keep things very constant here. Like that. And then we'll just, if we repeat the process throughout, we can have it accelerate and then decelerate. So again, if I just go in, make it, oops, here I'll put it a constant speed. Now slowly start decelerating. So I'll start favoring the drawing towards the end because it has to come to a halt and it will stop. Right.
Hey, Rohit, yeah, actually, I have one question.
Yeah.
Yeah, like in the below, you have like made the time chart.
Yeah.
So like we should do this first, like before the animating. Like we should like plan the timing this first.
Yeah, you can. I'll get to that as well.
Like because like it yeah, it will like help the like keeping the count of like how many drawing we like have to draw.
Yeah. So the thing with the timing charts is they're more of a communication tool because when you're planning the shot, even you, if you're, let's say, on a production, you're usually animating on 3 or 4 shots at the same time, you know. So if you rough out one shot and you have structured it in a certain way that you are slowing in from this frame to this frame and all those kind of things, and then you send it for a review and then you start animating on some other shot. And then once it comes back from the review, now you have to make some changes, but now you don't know which drawings to change, or if you start playing, you don't really know. So I think it's good to think in terms of timing charts, like as you go along. So even here, for example, before you started on, where was that? Yeah, if in this example, if you had to really start planning this out, what you could actually do is you could just have this chart at the bottom, just so that you know where the spacing is. Then you can just keep going. Like if it has 16 frames, you know, so I know this here, the frame number is 17, which might confuse a lot of you guys. It's because it is the 17th frame, but if from this frame to this frame, it's 16 frames. The window of time to reach from frame number 1 to frame number 17 is 16 frames. All right. So the 16 frames are usually from this frame to the one before the 17th frame comes. Right? Does that make sense?
Yeah.
So yeah.
I didn't get it. Like, why do we do that? Like, can it be just not like first frame and the 16th frame? Why does it have to be like 17?
But then it would be 15 frames. See, it would be okay. Let's take a look now. I'll just keep writing the numbers down.
So Rohit, can't we start the frames from 0?
You can, but it becomes very confusing because frame 0 is a misnomer, right? So
Okay.
so if you all right, if you look at my timeline below, as you can see from frame number 1, if we count 8 frames, right? So this window is 8 frames. So
But practically it's 7.
no, yeah,
It's 8.
I mean the window of 8 frames, as soon as this window ends, the last frame that comes up is the 9th frame, right?
Can I tell you something?
Yeah.
It's just imagine there are 16 boxes like frames. So box has like 2 sides. The first side will be added in the next one. So it's 70.
Yeah, you could
Simple
say
word.
that. So, oh God, is it getting very confusing for you guys? All right, for now, just think of it in this way. If frame number 1 to 8 is 8 frames, but as soon as those 8 frames end, the place where it reaches is the 9th frame. So the 9th frame is not necessarily part of the movement, let's say, but it is the end frame, right? So it took 8 frames to reach the 9th frame. Does that make sense?
Yeah,
Okay.
I get it now.
It makes sense.
Yeah.
Okay, so if something has to take 16 frames, so whatever frame number you're counting from, just add 16 to it. So it becomes that. Okay, so 16 frames from 1 is 17th frame, right? Is that all right?
Yes.
Yeah,
So
makes sense.
yeah, so it takes 16 frames for this ball to reach from frame number 1 to frame number 17. Okay, that much is clear. Now, before you start doing those ease ins and ease outs, you could start doing this chart, let's say, for example. So now you know that 1 in the middle would be what? 8 frames from 1, right? If the whole thing is 16 frames, so halfway would be 8 frames. So if you add 8 to it, it becomes 9, right? So it would be the 9th frame. And then again, if you go halfway, it would be 4 frames from it, right? Which would be frame number 5, right? Similarly, from here to here, if you go, what would be the frame number?
13,
Guys, what would be the frame number?
13,
15.
13.
It would be 4 frames from here to here, right? So it would be 13. So you keep breaking it down evenly. But as you can see, even though the timing, we are breaking it down evenly, like this is 4 frames, this is 4 frames, this is 4 frames, this is 4 frames. But the spacing of it, we've changed dramatically, right? So we keep slowing it down as it goes. So from here to here, then again, we made it favor the previous frame. So even though this is frame number 3, it is closer. Similarly, this one, this is frame number 15, but it is closer to 17. Similarly, then you keep on adding. So this will be 2. Does that make sense?
Yes.
Right? So, okay, this example might be very confusing for you guys to understand spacing. So let's not, I'll give you another example for it. Okay. So till now, this much was clear that for something to move, window of time is the number of frames it takes, and spacing is how those frames are put together. That much is clear. So now we were looking at if we have to think about how to space them. If we go straight ahead, which as we were trying to go here, we saw that we can't really manage the spacing if we go straight ahead, because we don't really know where exactly it has to end. So if we don't have two target drawings, let's say, we can't really decide where to put what. So now let's take the example of a bouncing ball, let's say.